Come with us now on a journey through time and space as we discuss stars in this amazing place.
I'm here in the foothills of the Himalayas to talk to you about the life cycle of a star.
Cox.
I've come to Albania to talk to Sir Adil III, who's a leading expert on nebulas.
A gas cloud is a denser than average region of interstellar medium, much like that cloud over there. Depending on the density, size and temperature of a given cloud, the hydrogen in it can be neutral, ionized or molecular. A molecular cloud is a region of space dense enough with hydrogen atoms that molecules, most commonly H2, can form. As far as we know, stick within these molecular clouds, sometimes called interstellar nurseries. A protostar is a star in the very earliest stage of development, when interstellar gas is still undergoing gravitational collapse and nuclear fusion as the core has just begun. A protostar is only 10 to 20 kelvins hot. The existence of protostars was first proposed and postulated by Soviet-American scientist Viktor Ambatorian.
Cox. Cox!
We're here in the Amazon rainforest to talk to you about giant stars. Now, a giant star forms when a regular star gets old and begins to run out of hydrogen. At this point, the core becomes more and more compact and gets hotter and hotter. After it reaches a certain temperature, it begins to burn helium as well as hydrogen, and this new heat formed begins to expand the surface of the star, pushing it outwards. If the star runs out of hydrogen completely and burns helium only, it begins to glow red, forming a red giant.
Cox.
I wanted to explain main sequence stars, so I came to Cambridge to talk to Paul.
Good. Main sequence stars, or as more commonly known, dwarf stars, are a continuous and distinctive band of stars. These stars are usually put on colour magnitude plots, also known as Hertzsprung-Russell diagrams or HR diagrams. The name for these derive from the creators of the Hertzsprung-Russell diagrams, which are, conveniently, Einar Hertzsprung and Henry Norris Russell.
Now, the Hertzsprung-Russell diagrams show the brightness of stars relative to each other. They range from things bright like a hyper giant to things not so bright such as a white dwarf. Our star falls somewhere in the middle of that. Good.
Cox.
So, wouldn't it be interesting if, much like people, stars came in different sizes, like giants and dwarfs? I'm under the bridge in downtown Uzbekistan to talk about dwarf stars with Professor Joshua Murray. A dwarf star is similar to any other star, only slightly smaller, and they come in all colours of the rainbow: red, yellow, brown, white and black, although black dwarf stars aren't considered true stars because they burn no fuel. In 1906, Hertzsprung discovered that red stars came in two different brightnesses much brighter than ours, these were called giants, and stars much dimmer than ours, and these were called dwarfs. To talk more about dwarfs, here is Joshua Murray.
It's an extremely tough time being a dwarf like me, because people are always picking you up and throwing you at things or at people, and other people are always like mistaking you for small infants or children, which can be so infuriating. only good thing about it is knowing that one day, when all of the outside fuels have been burned, you will literally implode into a small ball of matter. This then gets like extremely hot so quickly and causes you to expand.
Cox.
So in summary, this cloud is in many ways like our universe.
Now, Cox.
Hi, I've come to the French embassy to introduce a special friend.
Hello, I'm Jacques Pacage, and I am not wearing a shirt today, because science does not wear a shirt.
Now we're going to explain for you supernovas, which occur when a star decides to burn out rather than fade away. Usually, fusion provides a constant outward pressure, like so. But when this stops, the star begins to contract in upon itself. At this point, matter is projected outwards at speeds of up to 40,000 kilometers per second. Like so. It's in this way that most matter of the universe is formed, because only at times like this is heavy elements such as iron produced.
Yeah. Cox!
I've come to Alaska, the natural habitat of Gareth von Wolfswinkel, to explain neutron stars to you.
After a supernova, the core of the star remains, often in the form of a neutron star. After the surface matter is propelled from the sun, the extremely dense core is all that remains, the neutron star. Neutron stars are on average 20 kilometers in diameter, yet weigh more than our sun. In this high-density environment, electrons and protons combine to make neutrons. Hence, neutron stars.
Cox.
So we came to the Dead Sea. Can you see the black hole? No, neither can we, because even light itself cannot escape the gravitational pull of the object. Its density is so strong that anything would have to travel at faster than the speed of light to escape. Black holes occur when huge stars supernova, usually 10 to 15 times larger than our own sun.
Cox. Cox. Cox.
I'm here in the plains of Zimbabwe to explain the rebirth of stars. Now imagine I'm the centre of a solar system. I am the sun. As I end, I disperse all my heavy matter such as iron across the solar system. Now over millions of years, this heavy matter can then pull in the matter around it, contracting and forming new, even bigger areas of matter. At this point, it heats up and spins. After spinning for millions more years, eventually nuclear fusion occurs and the star is reborn.